Hi, and welcome to Linear Functions tutorial number 2. So last class, we worked with the graph of a line. We saw that a line could be either increasing or decreasing. We knew that to find whether it was increasing or decreasing, we could read it from left to right like we read a book, because everybody in the world reads graphs from left to right. Or we could choose to sign our name on the line, and if our name was going up, the line has a positive slope, and if our name was going down, it has a negative slope. We also talked about finding the rate of change. Slope, those two words are interchangeable, and we talked about finding two corner points, and then starting with the lowest corner point, and finding your rise by counting up, and then running over to meet your second point, which of course would be called your run. And so the rate of change, of course, refers to how much rise there is to the run. So that was last class. And so now we're going to talk about that linear functions can be expressed as a graph, as we've seen, or they can be expressed as an equation or a table. So right now we're going to look at the equation y equals 3x minus 2. And you're going to have to trust me on this, that this equation actually represents the same linear function as this graph does. So now we're going to focus on equations of lines. And so when we look at an equation of a line like y equals 4x plus 10, it actually tells us some things. This equation, y equals 4x plus 10, is actually in slope-intercept form. We'll learn about that in a little bit. But what it shows us is it gives us the rate of change. We don't even have to do rise over run. All we have to do is look at the number that's right in front of the x, and that is our rate of change. So for this equation, the rate of change is 4. Now, since 4 is positive, we know that the rate of change is increasing. So we're going to circle that. So that's what we're going to do today. We're going to be looking at equations of lines. So go ahead and write this equation down. I know it's not on your sheet, so write y equals 7x minus 2. We're going to look at equations of lines. Just identify the number in front of the x and say, wow, that's great. When it's in this form, the slope-intercept form, the number in front of the x automatically is the rate of change of the slope. 7's positive, so that means it's increasing. All right, let's keep doing this. I'm going to have to actually put that down. So write this next equation, y equals negative 5x plus 8. Once again, we're going to look at the number in front of the x. That is our slope. So our rate of change is negative 5. Since there's a negative, negative 5 is negative, that means it's decreasing. It's a rate of change that is decreasing. The next one, please write down y equals 1/2 x plus 7. And once again, we are going to look at the number in front of the x. We see that it's a fraction, 1/2. So the rate of change is 1/2, which we know means that this linear equation rises up 1 before it runs over 2. So the graph would be up 1/2, up 1/2. Now some people get confused because 1/2 is a fraction and it is smaller than 1, but it's still increasing because it's positive. So this one is increasing. All right, on your next sheet, go ahead and write down y equals x plus 3. And you'll notice that we always have been squaring, we're not squaring, but putting a box around the number in front of the x. And we're like, oh no, there's no number. What do we do? So when there's no number in front of something, we have to ask ourselves, well, how many x's are there? Because over here, right, when we saw the 4, we're like, oh, there's 4 x's, 7 x's. So here, there's nothing, but we do see 1 x, right? So when x stands alone, it's another way of saying that there's just 1 x. Kind of makes sense, right? If I'm going to give you an apple, I'm like, here's an apple. I'm not going to say, here's 1 apple. So same thing whenever we see x and it's just by itself. We're going to see it as x, but it will help us if we go ahead and put the 1 in its place so that we have something to put a box around. So the slope, the rate of change is 1. 1 is increasing because it's positive. All right, so go ahead and write this next one down, y equals 8. And we're like, oh no. There's no x. There's literally no x. So we can stop and we can rewrite this in a way that can help us. When there's no x, we can write that. There are 0 x's, and then we can put plus 8. Okay? When we do that and we put a box around the number in front of the x, we see that the rate of change is 0. Now, this is a tricky one, right? Because you don't see a negative, so you're like, is it positive? 0 is tricky in that way. It's neither positive nor negative. It's just kind of a neutral number. And so it's not increasing, it's not decreasing, it's neither. And when we get more practice with graphing, we'll understand why y equals 8 has a rate of change of 0 or slope of 0. And this last one, go ahead and write down y equals negative x plus 9. Once again, if I were to just pick up my blue pen and put a box around what's in front of x, all I would see would be a negative. I'm like, oh, where's the number? When you see an x, whether there's a negative or not, and you don't see a number, you know that number is 1. Negative x is the same thing as negative 1. And if I put a box around what's in front of x, that gives me my rate of change, negative 1, and since negative 1 is negative, that means it's decreasing. So what's our takeaway from this page that we just did? When the equation of a line is in this form, y equals mx plus b, which we'll learn more about later, we know that we can just scoop out that rate of change by looking at whatever number is in front of x. And then we can tell if it's increasing or decreasing by whether there's a positive or a no sign in front of it, because, right, like when I see a 4, there's no plus in front of it, but we know 4 is positive, or negative, and we actually see a negative. All right, so tables, I'm going to put the emphasis on tables of lines also show us the rate of change. So let's look at the first table that's on your sheet. So when I look at this table, I'm going, this is interesting. I'm going to look at the x part. Now the x part of a table, these are the input numbers. So let's remind ourselves that x is the input. That means we can put anything in for x, but our answer is the output, which is the y part of the table, right? So we can see that our input is going by ones. We're going down 0, 1, 2, 3, 4. Well, that's boring. But our output is doing something totally different. Our output is, okay, so I had to pause for a second there. So I guess I was talking about output. And as I look at this output, this is where the action is, right? The numbers are going 5, 7, 9, 11, 13. What's going on with our output? To go from 5 to 7, that's right, we're adding 2. 7 to 9, we're adding 2. 9 to 11, adding 2. 11 to 13, adding 2. So our rate of change with each thing as we're working down the table, right, we're going up by 2s. That's one way to look at it. Just look at the table, see, notice the patterns and how the patterns are changing, and then decide, well, it's positive, so it's increasing. Okay, so that's one way to do it. See what I have underneath here. Look at the y column to see if the table is increasing or decreasing. Okay, that makes sense. Or you can look at your rate of change. If it's positive, it's increasing. If it's negative, it's decreasing. Okay, let's look at this next one. So with this next one, once again, the input is boring. We're just going up by 1s. 0, 1, 2, 3, 4. It's the output that tells you what's going on with this linear equation. So we're going 9, 5, 1, negative 3, negative 7. It's kind of a little bit harder to see what's going on when we have the negative numbers. But look up here. What do we do? How do we get from 9 to 5? Well, we lost 4, didn't we? So 9 minus 4 is 5. 5 minus 4 is 1. 1 minus 4 is negative 3. Negative 3 minus 4, if you picked up your calculator right, would be negative 7. So when we talk about rate of change, we're talking about what's changing with the pattern as we move down the y column. Rate of change with tables, we look at the y column and we see what is changing with the pattern, or what is the pattern as each number's changing as we're moving down the y values. So we just said we're moving down by 4, and that's decreasing. Now, I do want to give you a second way to do this, because sometimes people are really great with patterns. They just see them right away, and they're done. Other people actually need a method. So actually, we're going to do that in the next one. I'm going to show you the method. Oh, no, I guess I'm going to show you this one because it says we always start our hoops from the bottom and go up. And you're just going to say, Miss Overby, what are hoops? All right, here we go with hoops. So with hoops, it's another way to figure out the pattern instead of just staring at it. So with hoops, what we would do is we'd start at the bottom. We'd say -7 minus -3. And I know what you're saying. Yep, that's right. Pick up your calculator. You can do it in your head if you want, but pick up your calculator. -7 minus -3 gives me a -4. Right? -3 minus 1, if I did that in my calculator, is -4. 1 minus 5 is -4, and 5 minus 9 is -4. So I know what you're saying too. It's like, why would we do the hoops when we can just look at it and tell? Some people like having a method. Down the road, we'll also have to pay attention to the x side of the table to get the rate of change. All right, so with this new table, we notice that once again, x is boring. It's just moving 0, 1, 2, 3, 4. The actions with the y, and we're like, what is going on here? 5, 5, 5, 5, 5. So let's look at the pattern. How are the numbers changing? What do you say? They're not changing. No, they're not, right? They are not changing at all. There's no rate of change. And what's another way to write no rate of change? That's right, just 0. And 0 is neither increasing nor decreasing. It's doing neither. So let's do the hoops. So we have a second method. 5 minus 5, 0. 5 minus 5, 0. That's right. That's a second way to find out that the rate of change is 0. That's right. Sometimes we can tell the rate of change from a table without even doing the hoops, and you are welcome to do that anytime. The hoops is just like a backup method to use if you can't tell just by looking. All right, now, oh no, I told you down the road, and here we are down the road already. The X column isn't boring anymore. Can you see that the input, it's not going up by ones. It's going 0, then 5, then 7, then 10, then 15. What this means is now we have to take into account what's going on the X side of the table. Let's go back real quickly to this one over here. The reason why we didn't look at the X side of the table is that if we did the hoops, we'd say 4 minus 3 is 1, 3 minus 2 is 1, 2 minus 1 is 1. There was no change in the X side. But there's change here, so we have to do the hoops on the left side. So 15 minus 10, 5, 10 minus 7, 3, 7 minus 5, 2, just making sure we're still going. 5 minus 0, 5. Now let's look at the right side at the y column. -11 minus a -6. If you pick up your calculator, you're going to get -5. -6 minus a -3. Well, that's going to be -3. -3 minus -1, that's -2, and -1 minus 4 is -5. Now, just a little side note, you will always, always, always be able to use those yellow calculators or any calculator throughout this Algebra 1 course. So please, pick it up, use it. All right, so here we go. What are we going to do? We've got a table with hoops on both sides, numbers on both sides, and we're going to remind ourselves that rate of change is rise over run, right? So that's why I'm showing you this. Rise over run is rate of change. Another way to say rise is the change in our y values over the change in our x values. So we're looking at, this is a change in my y value. This is a change in the x value. So the rate of change would be -5 over 5. And I know what you're thinking. Well, wait a minute. We also have -3 over 3. And you're right, we also have -2 over 2. But if you put all of these in a calculator, aren't you going to get the same thing? If I put -5 divided by 5 and hit enter, I'm going to get -1. Same thing with -3 divided by 3. I'm going to get -1. The rate of change here is -1. Because it's negative, it is decreasing. All right, so here are the linear equations that we've worked with so far. All of these equations are actually called, they're in slope-intercept form. And you don't have to know that term right now. It's just start to notice, yeah, these equations look similar. It's always y equals, there's an x, there's a number, sometimes there's not. But we've looked at all these equations so far, and these are a representation of what linear equations look like. But linear equations can also look different. So let's see what's underneath here. So they look different, but they're still linear. And so when we graph linear functions next unit, we'll understand why linear equations can be in different forms. When we see something like 3x minus 4y equals 12, we know that's in standard form. Still, it's a linear equation, but it's in standard form. When we see something like this one, it's a linear equation, but it's a very specific form called point-slope form. And sometimes you'll just see linear equations that look like that. It's not an official form, but it's still linear. So later on in this unit, we're going to be able to identify a linear equation from non-linear equations. So we're going to get really good at that. All right, so linear word problems have a certain look about them as well. Since linear equations do, linear word problems do. So here's an example of one. Kyle could do 5 push-ups when he was 1 year old. Okay, that's pretty impressive. Every year he could do 10 more push-ups than the year before. That's even more impressive and unrealistic. How many will Kyle be able to do when he is 20? So what makes this a linear word problem? Well, the number one thing is that the amount of push-ups that Kyle can do, they're increasing by a constant rate, right? Every year, 5 more. Every year, 5 more. It never says anything like, and then Kyle had a growth spurt, and that year he could do 55 more. No, every year, Kyle increases, not 5 more. Every year, 10 more. Sorry, I got confused there. Too many tutorials in a row. So the constant rate is 10. I said 5. I'm so sorry. Please forgive me there. So he started out being able to do 5, but his constant rate of change is 10. Every year, 10 more than the year before. So is there another way that we could check to make sure this problem is linear? Because sometimes people, like Miss Overby, can get their numbers confused. And I said, sure. Let's go ahead and say that on our input side, we can put x and y, but we can really know that our input side would be Kyle's age. And on the output side, that would be the number of push-ups that Kyle could do. So in the beginning, or not in the beginning, when Kyle was 1 year old, he could do 5 push-ups. At 2 years old, he could do 10 more than that. So 5 plus 10 is 15. At 3, he could do 10 more than that, so that's 25. So we could take the time and do hoops, and we could see we have a constant rate of change, or we could just look at our table and look at the y column. As we move down the y column, we are increasing by 10. So that is an example of a linear word problem. Here's another example. You've got a gumball tree in your front yard. It gives off 2,000 gumballs in the fall. Your mom feeds it a special formula that will reduce the gumballs by 100 each year. And how many years will it take before there are no gumballs on the ground to step on? So what makes this linear is that the gumballs are decreasing at a constant rate. They're going down by 100 gumballs each year. Is there another way that we could tell just by looking at and talking about it? Absolutely. We could do an input-output table, and we could say, in the beginning, before we started giving this tree its special formula, it would drop 2,000 gumballs, but by the next year, gosh darn it, if it dropped 100 less, and then the next year it dropped 100 less than that. And we can see by looking at the table that this is linear. Okay, so that's it. Just a real introduction to what linear equations look like, what linear word problems look like, and how to find the slope given the equation of the line. Thanks for joining me, and I look forward to seeing you in class.